Good morning. Welcome everyone to the EasyPower Thursday technical webinar. Before I introduce the guest speaker for today, I would like to run a couple poll questions and get some responses from the audience. We appreciate your participation and your attendance today. And let's see how this information kind of fits with your particular requirements. So our first poll question is going to have to do with what you're really familiar with. So what classes of medium voltage circuit breaker switchgear are you familiar with? So we appreciate your response. Obviously there's no obligation involved, but it would help us understand the audience and maybe guide some of our discussions as well. I would like to say that we've allotted some time at the end of Joe's presentation for questions and answers, and you're welcome to enter questions during the presentation, but it may be towards the end where we actually are able to address them. So it looks like we have about 2/3 of the people attending. Let's give this another 10 seconds to get your feedback. All right, and let's see how folks have weighed in on this. Good, we have a fairly good cross-section of the topic. And then the second question is, have you been involved with solid or gas insulated switchgear? And clearly that's probably going to be the area of most interest and focus of the new product discussion. So we do appreciate your feedback. That looks good. And here's how people have kind of weighed in on this one. So pretty evenly split. So Joe Richard is the U.S. launch manager for Schneider Electric's PrimSet switchgear. Joe graduated from Georgia Institute of Technology with a BS in electrical engineering in 2007, and he's been with Schneider Electric since 2008. He's worked in a variety of roles, including sales, marketing, and business development. Joe's main function has been medium voltage distribution switchgear and its applications, and his professional interests include power distribution, energy efficiency, power protection and automation, and energy storage and renewable energy. So with that, I'd like to change the presentation over to Joe. Take it away, Joe.
Thank you, Jim. Everybody should now be able to see my presentation.
Looks good.
Okay, great. Well, thank you, Jim. Just to introduce myself, my name is Joe Richard. I'm one of the offer managers and launch managers here at Schneider Electric, focusing on medium voltage materials, medium voltage switchgear in general. Today, we're going to talk about a couple of things, and the presentation is entitled Understanding the New Generation of Medium Voltage Switchgear. So here's the learning objectives for today. The main things we're going to cover, we're going to talk about the categorical types of medium voltage switchgear and how we're starting to think about the different types of medium voltage switchgear a little differently. We're going to talk about the differences and similarities between traditional medium voltage switchgear designs and new designs of medium voltage switchgear. We're going to learn about some design considerations for the newer types of medium voltage switchgear, and we're going to review a couple of examples at the end, especially around footprint designs and special design considerations. So I was happy to see in the poll that we're about 50-50 on people that have heard of or worked with either solid insulated or gas insulated switchgear, and people that maybe this is a new topic for, which is great. I'm glad to have the chance to introduce it to you. So in the medium voltage switchgear industry, we're starting to look at some different designs, different types of medium voltage switchgear. If you look at kind of the history of medium voltage switchgear, the current designs of metal enclosed switchgear fused switch style metal enclosed switchgear. The origins of those designs were in about the 1950s and 60s. More modern metal-clad withdrawable vacuum circuit breaker medium voltage switchgear designs had their origins in the late 70s, and for a lot of companies currently selling them today in the early to mid 80s. And to tell you the truth, designs haven't changed a lot on those two broad categories of medium voltage switchgear until I would say maybe the past 10 years, when switchgear manufacturers have started to develop newer types of medium voltage switchgear and newer applications of the existing styles of medium voltage switchgear. So when we're talking about medium voltage switchgear today, we're really kind of grouping it into three main large categories. And the way these are categorized is by dielectric insulators. So the first style is air insulated switchgear, or AIS. Most of the traditional styles of medium voltage switchgear, both metal enclosed and metal clad switchgear, falls into this variety. Things like withdrawable vacuum circuit breakers in metal clad style switchgear falls into the grouping of air insulated switchgear. In general, these are larger, very customizable, using withdrawable style circuit breakers, as I've mentioned, and take a design philosophy of ease of maintenance. It's easy to take the breakers out, work on those breakers, leave the bus live, and put the breakers back into place, and have very large open designs. And we'll talk about why, I'll talk a little later about the good things and the bad things about this style of design. If we move to the right, we're moving to a little bit newer style of switchgear, gas insulated switchgear. Gas insulated switchgear has been prevalent in the high voltage and utility market for quite a while, but started to see some entrance into the medium voltage market. And when I say medium voltage, I'm talking about anything from 1,000 volts up to 38,000 volts of nominal voltage. GIS started to see its entrance into the medium voltage market sometime in the 90s, depending on where you were, either in the world or in the US. This is much more true in the utility side of the business. But as of the past decade or so, gas insulated switchgear has become much more prevalent in a handful of power critical markets, even in the industrial side and even in the heavy commercial side of the US. And we'll talk a little bit more about the kind of the advent of gas insulated switchgear. But some of the major differences, or the largest difference, is that the main insulating dielectric, or the main insulating material used in gas insulated switchgear, is some kind of pressurized gas. Whether that's the more traditional SF6, and we'll talk a little bit more about what that is, or if it's a newer style or a newer dielectric gas being used. Some of the benefits here are a smaller footprint, much more modular design, a sealed from the environment design, a sealed for life tank for the actual circuit breaker, and this is especially advantageous at higher voltage ratings, at that 2738 kV class medium voltage switchgear ratings. If we move to the next category to the right, we're talking about the newest style of medium voltage switchgear, and this is a style we're referring to as solid insulated switchgear. Generally, an epoxy or a rubber-based solid insulator makes up the primary form of dielectric insulation in this style of gear, as opposed to gas in GIS or air separation in AIS. It has a lot of the same characteristics as gas insulated switchgear, in the sense that some of the biggest benefits are the modular design and very small footprint, and it brings with it a very long maintenance cycle. So reduced maintenance cost is also a great benefit of solid insulated styles of switchgear. And you can see kind of an evolution of design styles here, going from AIS to GIS to SIS. Now, if we look at, I think it's always important to kind of talk about codes and standards a little bit, and kind of where we are with the IEEE codes and IEEE ANSI style codes. Currently today, the most prevalent two codes in medium voltage switchgear are the C37.20.2 and C37.20.3, and these are codes that govern the recommended ratings, the testing standards, and the construction standards specifically around metal-clad switchgear and metal enclosed switchgear, respectively. Other important standards that are often considered or need to be taken into consideration are the medium voltage breakers standards, C37.04, which covers the rating structure for all medium voltage and high voltage circuit breakers, including continuous current, dielectric withstand, short circuit current, transient recovery voltage, capacitive switching, along with mechanical endurance, load current, and out of phase switching. C37.06, which lists the preferred ratings for medium and high voltage circuit breakers, and C37.09, which is the design and production testing procedures for medium and high voltage circuit breakers rated above 1,000 volts. So these medium voltage circuit breaker standards really apply across the board for the MV switchgear standards when it comes to using circuit breakers as opposed to fuse switch style interrupting or disconnecting. Other important switchgear standards, though, I think we need to mention are the C37.20.7, which is the IEEE guide for testing for arc resistant, or as the switchgear standard is called, testing metal enclosed switchgear rated up to 38 kV for internal arcing faults. And when you hear a manufacturer state that their switchgear is arc resistant, what they're saying is they have tested their switchgear according to this standard, and that it is passed to some degree to which they should be able to tell you the type of test that they passed according to this C37.20.7. So I think this is something that's often confused, but I think the important thing to know is if the term arc resistant is used according to an MV switchgear, then what they're saying is that they passed this test or they've tested according to this standard. And as usual, it's in our industry, it's usually important to end users as well as local jurisdictions that it has a UL labeling that it was tested according to this standard in order to be called arc resistant. And then looking forward a little bit, I think it's important for me to introduce this new standard that's in the draft stage right now that the IEEE standards committees are working on, C37.20.9, which is the IEEE standard for incorporating gas insulating systems into metal enclosed switchgear. It's a standard that's been in the draft stage for several years and is still being worked on, and will soon be the standard which all of the gas insulated switchgear, at least for medium voltage applications in the US, will need to be designed and tested and rated according to. So keep an eye out for that newer standard that should be released, I would say probably within the next couple of years. So one question I often get is, and is not necessarily easily understood or is often understood, is what's the difference between metal enclosed switchgear and metal clad switchgear, and why would I as a switchgear manufacturer rate one type of my switchgear according to one versus the other? So I often like to think about this kind of as in terms of the fingers and thumbs analogy. All thumbs are fingers, but not all fingers are thumbs. It's very easy to say that, to use that analogy in the sense that all metal clad switchgear, which is the withdrawable style circuit breaker switchgear, is a type of metal enclosed switchgear, but not all metal enclosed switchgear is metal clad switchgear. I think that's kind of the easiest way to think about it. The metal enclosed switchgear standard is more of a ratings and testing standard with very minimal construction requirements. It's more based around giving recommended ratings so that different types of switchgear have similar rating values, so they're easier to compare to each other, as well as giving minimum test standards, both in terms of design or type tests and production testing. And then it does give some minimum construction requirements around sizing of bussing, spacing of bussing, and some materials and finishing that's required. Metal clad switchgear actually piggybacks on top of the metal enclosed switchgear standard and takes it much further in terms of the construction requirements. So if you ever wondered why most manufacturers' metal clad switchgear looks very, very similar, this is why. It's because the metal clad standard is very much a build standard. It very much explains how to build metal-clad switchgear and how it needs to be built. And certain things like withdrawable circuit breakers, automatic shutters and stabs, insulated copper bussing, compartmentalizations, the required for MOX and TOX, and the materials and finishes, and the wiring sizes and types for all of the control wiring. All of those are basically laid out type for type and exactly how they need to be installed and constructed in the metal-clad switchgear standard. So in one sense, it's very good. And it was really written by the utility industry so that they could compare different manufacturers' metal-clad switchgear and get a very apples-to-apples comparison. The problem with the metal-clad switchgear standard is it doesn't leave a lot of room, or any room really, for innovation and change. There are some newer styles of metal-clad switchgear that have recently come onto the market in the past couple of years, and generally they involve trading ratings for footprint, and some different sizes of circuit breakers, and but they still follow this general construction standard and are kind of limited and barriered into this build standard. So newer styles of switchgear, the GIS and the SIS that we're going to talk a little bit more about, have traditionally adhered to the metal enclosed switchgear standard because it's a broader standard and allows for a lot more change and innovation. So that's kind of an overview of the standards and kind of where we are, where we're going, and kind of reasoning behind why different types of switchgear are going to be rated to either metal enclosed or metal clad. So let's take a look at traditional metal clad, or what I'm going to refer to basically for the rest of the presentation as traditional MV switchgear, as traditional metal clad switchgear. Here's a good kind of profile view of what a slice of metal-clad switchgear looks like. Generally, two high construction breakers on the top or the bottom. This can be limited a lot by the current ratings, the heat dissipation requirements, and a lot of times the voltage ratings can limit between 1 high and 2 high. But generally, in applications at 5 and 15, and often at 27 kV, you can do 2 high construction. At 38 kV, I think all the manufacturers that I've seen have been limited to 1 high construction. We average about a 36-inch wide by 90 to 100-inch depth and footprint. You have a nominal bus insulation, basically an electrocution kind of barrier coating around the main busing of the switchgear that is required by the metal-clad standard. But I think the key thing to keep in mind here is that the dielectric ratings, the dielectric calculations, are all done using air gap, as opposed to using that kind of nominal insulator around the main busing. It requires both front and rear access for where the cable entry is going to be. A very open and easily accessible design, and a very customizable design. And this is good in the sense that if you need to be able to bus up to existing switchgear or do some custom busing entry applications, metal clad is probably the best option for you. But the big difference between the philosophies of ease of maintenance versus less maintenance, by having a kind of open and exposed busing area and especially an open and exposed circuit breaker, means that the rear of that circuit breaker, the operating components of that circuit breaker, is open and exposed to environmental contaminants, things like moisture and dust, chemicals, rodents and snakes and things that like to crawl into switchgear to stay warm in the winter. All of these kind of environmental considerations that contribute to switchgear failures or switchgear lifetime degradation. That's kind of the trade-off between ease of maintenance versus having a more enclosed style. Looking at the circuit breaker design, there's 3 main components: the pole assembly in the rear, the operating mechanism, usually in the front, sometimes in the bottom, depending on the manufacturer of the circuit breaker, and then the breaker truck in the bottom that is easy to makes it easy to kind of roll the breaker in and out. If we look at newer designs of medium voltage switchgear, this is an example of gas insulated switchgear. So one of the first big differences here is with the newer styles of switchgear, we're looking at fixed mounted circuit breakers as opposed to withdrawable circuit breakers. And the trade-off there being obviously the maintenance factor, the ease of withdrawing the circuit breaker in order to get to it and operate it. Most of the gas insulated switchgear designs are single high construction. With GIS applications, you can get as small as 24 inches wide and 55 inches deep. And this is true all the way up to 38 kV. And at these higher voltage class ratings, that's really where this style of switchgear shines, is at these higher levels. The SF6 gas insulator is what's used as the main dielectric throughout the gear in order to calculate phase separation and phase differences. SF6 is used in those calculations as opposed to air separation. With gas insulated switchgear designs, they're often front access only, so that the cable entries as well as the operating mechanisms are all in the front of the gear, and even installation can be done completely from the front of the gear. It uses a very modular design of architecture, and when I say modular, I want you guys to think of basically switchgear Legos. If I need a main, a feeder, a tie breaker, I have a set architecturally designed cubicle to use as that style of operator, and I can build out my entire lineup basically by picking the types of cubicles I need and putting them together. You're always going to have a common busing standpoint. You're always going to have a common cable entry point. It's not going to change from compartment to compartment or type of switchgear to type of switchgear. So it's very easy to do an entire lineup design that way. One of the biggest benefits of this style of switchgear, and you really get this from the fixed circuit breaker style, is the environmentally sealed option. Basically meaning that some of the main operating components, the actual circuit breaker, the vacuum or SF6 operating bottles, things like internal disconnect switches and internal ground switches are all sealed away for the life of the switchgear inside an environmentally sealed tank. And this means that even though it's more difficult to do maintenance is required much less. So with GIS or SIS styles of switchgear, we're looking at 10-year maintenance cycles as opposed to yearly maintenance cycles on air insulated styles of switchgear. So that is really the trade-off, is you're looking at a style of switchgear that requires less maintenance, is more reliable over a long period of time, and we're looking at reducing that total cost of ownership. If you look at the breaker on the bottom left, it looks fairly different, but the main components are the same. So you'll have the pole assemblies in the rear, the operating mechanism in the front, and since it's a fixed mounted circuit breaker, it's not going to be withdrawn, so you don't have to have a truck underneath it. So I see we got a question here. Are breakers gas insulated as well in a gas insulated switchgear? So with gas insulated switchgear, you often have both options. And for those that aren't so familiar, I like to distinguish between the insulating medium, which is the gas, and the interrupting medium, that would be the bottle. So within the bottle of the circuit breaker, you can interrupt in a vacuum circuit breaker bottle and still be SF6 style insulated switchgear. Or often you have the option for an SF6 style interrupting bottle in SF6 style insulated switchgear. So it's important to distinguish between those kind of two different types of, whether it's the insulating material or the interrupting material. So really good question there. Okay, so let's move on and look at now solid insulated switchgear. So it looks very similar to the gas insulated switchgear in kind of the architectural style. Fixed mounted circuit breakers, single high design, but now we're shrinking down even smaller into the 15-inch wide range and 36-inch deep range. So we're getting even smaller than the gas insulated switchgear. This is a style that Schneider Electric makes called the Prim Set that we're using EPDM rubber as the insulator, but solid insulated switchgear designs can involve an epoxy, it can involve an insulating rubber. There's a various number and different styles of solid insulating material, and I'll talk a little bit more about that in a bit. They have both front and rear access designs, but we do have designs that are available for front access only. So if you need to put it up against a wall, very similar to the gas insulated switchgear, those are optional. Environmentally sealed, very similar to the gas insulated switchgear. All of the electrical components, all the current carrying components, as well as all of those moving components of the circuit breaker and internal disconnecting grounding switches are sealed away and environmentally sealed from all those contaminants that we talked about before, either in the solid insulator itself or inside of a solidly insulated circuit breaker tank. And again, solid insulated switchgear has the modular design built in with it. So it's very easy to lay out and design an entire lineup of solid insulated switchgear. If you look at the circuit breaker in the bottom left, it looks very similar. You're still going to have vacuum bottles or vacuum poles for the actual interrupting and an operator mechanism in the front of it. So let's talk a little bit about those insulating materials. And most of the time when we're talking about gas insulated switchgear today, we're talking about SF6 or sulfur hexafluoride. It's a gas that's been used for a long time in the electrical industry as a dielectric material. It's inorganic, colorless, odorless, non-flammable, non-toxic, non-corrosive. Obviously a very strong dielectric. It's thermally conductive, which means it's going to transfer heat to allow for heat dissipation of the switchgear fairly easily. And it has a self-healing property in the sense that when an arc happens inside of SF6, it does break down the molecule, but the molecule naturally wants to recombine and come back together. SF6 is used in a wide variety of industrial fields, everything from semiconductor manufacturing to medical imaging, microwave systems, and it's even used in science classrooms. You can go on YouTube and find images or videos of high school chemistry teachers talking about air density, and they'll do one presentation with helium and make their voice go and breathe it in and make their voice go up very, very high to explain air density. And then they'll breathe in SF6 gas, and because it's a very, very heavy gas, their voice is going to drop down, and they kind of sound like a monster for a little while. So in that sense, it's a very common gas to be used. The one downside to using SF6 gas is that it's a very, very potent greenhouse gas. It has something like 2,300 times the greenhouse potency of CO2. So that is something that is important to keep track of with SF6. Once this was kind of realized and it became an important topic in the 80s and 90s, a lot of the high voltage applications and the medium voltage applications that it was starting to be used in started to pay a lot more attention to SF6 leakage and escaping into the atmosphere. And the industry's come a long way. Between 1990 and 2013, while the nameplate capacity of US SF6 devices has almost doubled, the rate of escapage has dropped by 87%, which is a really great to see that the utility industry, the electrical distribution industry has taken some great strides in really managing this gas. And it's important, I think, to know that most of that escapage happens because of SF6 gas handling on site. Either you have to install the switchgear and then fill it with SF6 gas, or you have to remove the gas at some point for maintenance procedures. In the medium voltage range, while that's hard to escape in the high voltage world, in the medium voltage world, it's very easy for us to provide SF6 switchgear that doesn't require any SF6 handling on site, doesn't require either draining or refilling tanks for maintenance procedures. So when you're considering using gas insulated switchgear, I think it's important to consider switchgear that SF6 is filled at the factory and doesn't require any on-site managing of gas. All right, so let's look at solid insulating material. So these are much more common and have been used for a long time in terms of types of insulators, especially in metal enclosed and metal clad switchgear. But it's important to know that when we're talking about solid insulated switchgear, we're using some of the either more robust types or some of the newer types of switchgear. And these usually fall into the silicone rubber, epoxy resin, EPDM rubber styles or types of solid insulating material. And I think when you're trying to compare different types of solid insulators, that dielectric constant is an important factor. It's basically a ratio of the permittivity compared to the permittivity of a vacuum. So if you're talking about air is going to be about a 1 dielectric constant, and obviously the higher up in number you get, the more dielectrically resistant the material is, and the better the material is going to be. But there may be other factors that need to be taken into consideration, such as thermal conductivity for heat dissipation, degradation due to environmental factors, and kind of the long-term life expectancy. So these are all the things that are considered with when manufacturers are trying to pick the solid insulator they're going to use for solid insulating material. And I think it's important to realize that all of these materials I have listed here and all the ones that are used in solid insulated switchgear are types of materials that have been used for quite a long time. The difference is that now we've gotten to a level of manufacturing preciseness, and we've been able to develop manufacturing processes that allow for much tighter tolerances in terms of installing or applying these solid insulators to conductors or around the conductors that need to be insulated. And when you think about the type of technology that it takes to do solid insulated switchgear, you're actually talking about very similar technology to what's being used on medium voltage distribution cable. This would be ground shielded medium voltage cable that we've actually been using for quite a long time. We basically have been able to take that style of technology and use it inside of the switchgear, letting us shrink down that footprint and get a much longer lasting, more reliable, lower maintenance style of switchgear. So these are kind of the different things we like to consider or that need to be considered when designing solid insulated switchgear. I see you got a couple more questions. I'm going to kind of run back and address these real quick. What is the cost difference between metal clad and metal enclosed switchgear? It often depends much more on the type of disconnector. So if you're talking about a metal, or if you're talking about a circuit breaker versus a fuse switch, the circuit breaker is going to be quite a bit more expensive. Usually in the range of double the price compared to, say, a circuit breaker. The fuse switch is going to be quite a bit less than the circuit breaker design, but it very much depends from type to type and manufacturer to manufacturer. So I wouldn't take that 2 times number and go do a budget with it. You always want to ask a manufacturer to give you a budget on the type of switchgear you're going to use. Are you aware of any specific utility that does not accept SF6 gas as an insulating medium? Yes, there are some utilities that have decided that they don't want to use SF6 gas as insulating mediums. I know several on the West Coast have made that decision, and I think there are a few in the Midwest and the northern Midwest that have made that decision as well. The EPA does regulate SF6 on a voluntary basis, but most of the utilities have gone ahead and signed up for that voluntary reporting program that the EPA runs. None of it is required. It's all completely voluntary, but most utilities, I think, have signed up on that right now. And pretty much every utility out there that deals in transmission level voltages uses SF6 to some extent or another. But the real question is, once we get into the medium voltage range, whether the utilities use it or not. Most utilities still are using and applying SF6 gas because it's really is still the best option out there in terms of reducing footprint and decreasing maintenance cycle on larger voltages when we're talking about the 27, 38, and even higher voltage classes. There are some alternative gases that are just starting to appear on the market. They have their own drawbacks, whether in terms of life expectancy, toxicity. Depending on the type of gas you're looking at, there's always a trade-off. But there are some newer designs of GIS that are starting to come onto the market that use either dry air or some other type of inert gas like nitrogen or something like that, that are kind of peeking their head onto the market, but still are a little, I would say, a couple years away from being more accepted in general on the market. All right, so let me keep going. I see some more questions popping up, but I'll jump back to these as we get kind of towards the end of the conversation, and we'll come back to those. So I've mentioned several times this idea around a modular switchgear architecture in terms of the lineup. I'd also like to kind of mention that this is very true in terms of section to section design. If you're looking for kind of a similarity of types of cubicles, it's very easy to find this in the newer styles of medium voltage switchgear, GIS and SIS. Common busing points, common positions of low voltage compartments, a common point for the fixed mounted circuit breaker, similar positions for cable entry and instrument transformers. So if I look at, this is an image of the solid insulated switchgear I was showing you. You can see busing on top, circuit breaker below that, instrument transformer compartment in the very bottom, and then that operating mechanism, low voltage box, and cabling on the front of the switchgear. If I do kind of a similar comparison for gas insulated switchgear, you can see it lines up very, very similarly. So when you're using these kind of modular designs of switchgear, it's very easy to design the layouts because of all these common points for bus connection, cable connection, and operating equipment. It's very easy to kind of know where this is going to be, choose the types of sections you need, lay out the lineup that you need, and possibly without even needing to contact the manufacturer, you could probably, from the catalogs of these products, be able to know the size, dimensions, and necessary placement for an entire lineup of medium voltage switchgear, making design projects a lot easier and a lot more simple to kind of lay out and reserve space. So let's talk a little bit about some other considerations with these newer designs of medium voltage switchgear, and some of these considerations actually are starting to apply to traditional styles of medium voltage switchgear, including metal clad switchgear. So let's talk about some different insulating or instrument transformer types, low power devices, things like low power voltage transformers, low power current transformers. In the voltage transformer world, there's a couple of benefits from going to these low power devices. First of all, by going to sensor style devices, we're able to remove requirements around primary fusing inside of switchgear. When you look at metal clad switchgear, the most common failure point inside of metal clad switchgear is either VTs or CPTs, and usually due to winding failure and usually due to environmental contamination over time. When you look at capacitive dividers or resistive dividers as alternatives for low power voltage transformers, you don't have the same types of failure points that you do with traditional inductive style wound transformers with CPTs and VTs as they are today. So you're able to remove a lot of those common failure points and get a longer lasting, more reliable style of instrument transformer. Looking at the current transformers, some similarities to the low power voltage transformers, but really some of the benefits we get here are lighter weights, smaller footprints when we go to things like Rogowski coil CTs, as well as higher levels of accuracy or more linear designs of accuracy. And when I say more linear designs of accuracy, I mean that you don't have to worry as much about the ratio of the CT, whether it's 100 to 5, 200 to 5, 500 to 5. With things like Rogowski coil CTs or even iron core LPCTs, they have linear secondary outputs, so that for the entire range of application, you're going to get a very accurate reading. Whether you're reading at 100 amps or 600 amps, you're going to get much more accuracy out of the newer designs of CTs. Now, the downside right now on the market today is a lot of these products are proprietary, and they have to be used either with particular styles and manufacturers of meters or particular styles and manufacturers of relays. I have seen low power voltage transformers on the market today that are not proprietary, that can be used with anybody's relays and meters, and they usually involve some type of amplifier system. I have yet to see any low power CTs that are proprietary. Most of the ones that I've seen, or all the ones I've seen on the market today, have to be applied to a specific type of meter or relay. So just keep that in mind if you're looking to use these newer styles of instrument transformers. Cable connections are changing. with these newer styles, the GIS and the SIS styles of switchgear, we look into using elbow styles of connection as opposed to the traditional NEMA 2-hole lug connections. And the real big benefit here is that we're removing the exposure to potentially live components in the cable compartment. We're completely insulating even the connection point for the cables, which grants a huge benefit around safety and reliability. It also lets us shrink the footprint quite a bit of the entire switchgear package if we can move those cables a lot closer together. The downside here is that generally these elbows have longer lead times than more common stress cones and cable lug connections. And it's important that you know the type and size of cable that you're using to make these connections, because a lot of the elbows don't have a lot of width or a lot of versatility in the width of cable that can be used for. It's important to order the correct cable elbow for the correct size of cable that you're going to be using. And when I say size of cable, I don't just mean the size of the conductor. I mean the width of the conductor plus insulator overall on the cable. It's important to match those correctly. So while this brings a big benefit around safety and reliability, it basically just means that the ordering of the cable connections needs to move up in the timeline of the project. So it's just an important consideration. So we've kind of talked about a lot of benefits of GIS and SIS compared to traditional styles of switchgear, but I think this is one of the biggest ones, is when you look at the IEEE 493 Gold Book. It's basically a utility study done to analyze what were the most common causes of failure with metal-clad switchgear. And so I'm putting this into the common causes of AIS switchgear. And there's a lot of big ones on here. Exposure to moisture is very high up there. Deterioration due to age, exposure to dust and other contaminants, malfunction of the protection device, thermocycling, basically the heat and cold cycle that it experiences. These are all large contributors. If I look at which of these contributors are applicable to AIS, but not applicable to GIS, SIS, things like mechanical damage from foreign sources, exposure to all those environmental contaminants, and even the normal deterioration caused from age in AIS, which is reduced in GIS and SIS styles of design, we can eliminate greater than 50% of the main failure points, main causes of failure with traditional styles of gear by using some of the newer styles of switchgear, things like GIS and SIS. So at the end of the day, that's the whole point. We're trying to develop newer styles of switchgear that are going to last longer, be more reliable, require less maintenance, as well as increase safety and decrease the amount of footprint that's required. So when you're trying to decide which type of switchgear is good for me or is right for my project, here's kind of a good chart. I won't spend too much time on this because we're going to share this presentation with you after this. But just good things to consider if you're looking at ratings, which type of switchgear is going to fall in, is going to probably be the best application for you. Whether the important thing to your application is footprint or maintenance or arc resistant designs or environmental hazards. These are all good things to consider when you're trying to choose the type of switchgear for your application. Other things to consider, differential protection. With newer styles of design, it's more difficult to do differential protection due to limitations on types and amounts of CTs that fit into the switchgear. But with GIS and SIS, one of the main points is to help prevent face-to-face crossover with these more modern insulating systems. So the question really is, do you need bus differential protection with these newer styles of switchgear? At the end of the day, that's up to you as the designer. But then the question is, could I use a low impedance bus differential system as opposed to a high impedance and be able to share some of the CTs between normal protection and bus differential protection? Close coupling is an important thing to consider. With a gas insulated switchgear, I'm not aware of any close coupling capability. With solid insulated switchgear, some allow it, some don't. So it's more prevalent with cable connected designs. And then control power is an important thing to consider. With these newer styles of switchgear, a lot of times you don't have the option for a CPT. So we need to make sure that we're designing for control power either from a downstream panel, the secondary of a transformer, a battery system, if that exists in your design, or maybe a UPS somewhere in the design. So we just need to make sure that's part of the design consideration. I had a couple more questions I'm going to run through real quick. Let's see. With Rogowski coil CTs, let's see, I'll go back to the top. Why aren't voltage dividers used in metal clad? I've actually seen some designs where they are being used in metal clad. So I think that's newer to the market, but I think you'll see more and more of that. What is the time frame for SF6 to be tested? I'm not quite sure. So SF6 is already on the market today. And as I showed you before, there's a new standard coming out in which it'll lay out production testing, design testing, but it'll be very similar to the metal enclosed. So SF6 is available today already on the market. With Rogowski coil CTs, do the conductors have to be perfectly centered for proper reading? Actually, my experience has been that it's kind of the opposite, that they actually allow for more flexibility in terms of the design and where they fit on the busing than traditional inductive style CTs. What's the function of the amplifier? Amplifier design. So with low power CTs and specifically with low power VTs, they're actually putting off, they're not putting off a 120 volt signal. They're putting off much smaller voltage signals, usually in the range of millivolts or millivolts to single volts, and so it needs to be bumped up to a 120 volt signal for it to be a kind of universally accepted. So that's the main function of the amplifier, is to bump up that voltage signal to a more universally accepted peak signal. What's the maintenance cycle for solid insulated switchgear? 10-year maintenance cycle on both GIS and ISIS versus yearly maintenance cycle on metal clad. And then with elbows, how would I land 6 500 MCM cables per phase? So often what you're going to do with that kind of design is you're going to split and do a parallel installation. First of all, you can stack the elbows up to usually 2 or 3 deep, and several designs of either GIS or SAS have parallel connections. So where you will have a bushing for ABC phase, you'll have a parallel bushing for ABC phase, so you can stack multiple cable connections that way. So some good questions there. All right, I'm going to keep moving because I want to try and get through some space savings examples that I have here, and then we'll do a little bit more question and answer at the end. So let's consider this 15 kV lineup. Main breaker, 5 feeder breakers, a single VT associated with that main breaker. This is a very traditional basic radial main and feeder lineup. If I was doing this design with metal clad, this would look like 4 2-high sections. You'd use a main and a VT in the first cubicle, and then 2 sections of 2 high breakers, and then 1 section of a single high breaker. NEMA or NEC required working clearance in the front and in the back. So if I'm looking at the total footprint for switchgear plus NEC required working space, I'm looking at 211 square feet of space for this 15 kV application. If I do the same application with gas insulated switchgear, now I'm looking at a design that's front access only, 1 cubicle each for the circuit breakers, and then a VT section underneath the main breaker on the far left. NEC working clearance on the front, but just basically heat dissipation space on the back, looking at 130 square feet of space. So quite a bit of reduction versus that 211 square feet. If I take this even further and design this with an SIS, again, 6 sections, 1 section for a 1200 amp main, multiple sections here on the end for 600 amp feeders. So being able to get more load appropriate size breakers if I'm using SIS designs or even GIS designs, with the available 600 amp breakers as opposed to only 1200 amps. VT sections below that main breaker, NEC working clearances on the front, heat dissipation and cleaning aisle in the back, looking at 82 square feet of space. So comparison between the 3, with that gas insulated switchgear being able to reduce by about 40%, and with the solid insulated switchgear being able to reduce that footprint by just over 60% compared to the traditional metal clad lineup. So a pretty big reduction in space. So that's a 15 kV example. Let me look at a 38 kV example. This is 34.5, very common voltage. At 38 kV class. Again, a radial switchgear design, main and 4 breakers, VTs associated with that main. Basic relay protection. If I look at this in 38 kV design, now I'm looking at quite a bit larger size of metal clad switchgear to bump up to 38 kV. 5 sections, 1 2000 amp breaker main, 4 1200 amp breaker feeders, VTs withdrawable above the main, NEC working clearances front and rear, looking at a total of about 456 square feet of space, quite a bit of room. If I do this with the gas insulated switchgear design, very similar, exactly the same one line layout, 2000 amp breaker main for the 1200 amp breaker feeders, VTs below the main, NEC working clearance in the front, and heat dissipation / cleaning aisle in the rear, looking at reducing that down to 143 square feet of space versus that 456 square feet with the metal clad. So a pretty big reduction there. So if we're comparing those two, metal clad versus gas insulated switchgear, looking at almost a 70% reduction in footprint. So some real big space savings here possible with a newer design of medium voltage switchgear. I don't put an SIS example with this because the metal enclosed SIS designs I've seen so far only go up to 15 kV. So once we look at that 27, 38 kV options, we're looking at gas insulated switchgear only for those options. So some pretty big footprint savings. So I'm kind of getting to the end here of my presentation with a couple of minutes left for question and answer, which is great. I want to end on this slide, and this is, I think, is just a great kind of a slide to have with you, or put on your desk when you're trying to think, okay, I'm starting my new design of medium voltage distribution. What are the things I need to ask myself when I'm trying to choose the type of switchgear that I need to use? Well, these are the questions you should ask: footprint and layout, good questions around protection and controls, good questions around safety. What are my requirements around safety? Excuse me, obviously electrical requirements, voltage, current, interrupting ratings, the common requirements around the switchgear. Environmental application. I think this is sometimes not paid as much attention to, but I think these are important questions to ask yourself. What kind of heat, humidity, temperature ratings do I need to be able to withstand? What kind of chemical contaminants? And inside of this, I would also think of things like dust or any kind of any other types of physical or chemical contaminants that may exist in the area. And then an important thing is to think about also our friendly little rodents and vermin and insects that may be present in the area, or that may be a common problem in whatever facility that this switchgear is going into. So good, important environmental questions to ask yourself. Equipment coupling, we kind of talked about that. And then what are the requirements around reliability and cost? And I think in that reliability question is around maintenance. Am I designing for a customer that has qualified MV electricians on site that are going to have the ability to maintain their switchgear on a regular basis as it should be maintained? Or is this customer basically already treating their switchgear like set it and forget it style switchgear, like we find a lot of our customers are already doing? If that's the case, maybe I should consider giving them a longer maintenance cycle style of switchgear, a more reliable design of switchgear. So all good considerations, kind of questions to ask yourself when you're going into a design phase with medium voltage switchgear. And with that, I'm going to take a look at the questions that I haven't gotten to yet. If you have any more questions, please feel free to put them in the chat, and I'll kind of get to them in order. And if we run out of time, then I'll answer the questions, and Jim and the EasyPower folks can get you my answers after the webinar. So I'll just keep going down the line here. So what is the cost premium on GIS or SIS? So it very much depends on the voltage class that you're using. I would say with GIS, if you're applying it at the 27 and 38 kV voltage classes, it's pretty much on par with metal clad. The costing is going to be about the same. If you're applying at the 5 and 15 kV voltage classes, the GIS is going to be it's going to be a significant price adder. I would say somewhere somewhere in the range of 30%, I would say, to move to the GIS and the 5 and 15 kV. The SIS, however, is very cost comparable to metal clad switchgear at the 5 kV and 15 kV applications. So oftentimes we find customers that are interested in these newer designs of switchgear, like the SIS for 5 and 15 kV and the GIS for 27 and 38 kV. Next question is, which type is beneficial for MV between 4 kV and 15 kV 600 amps? I would definitely point you towards the solid insulated switchgear for those ratings, 4 kV to 15 kV 600 amps. You're going to be more cost competitive versus metal clad switchgear, and you're going to save quite a bit of footprint compared to metal clad. Your comparison chart shows greater than 15 kV, greater than 1200 amps. So as I kind of just mentioned, at the 5 and 15 kV levels, your solid insulated switchgear is going to be probably your go-to, and that 27, 38 kV gas insulated switchgear. And then the question is always around, what are the other requirements around maintenance, reliability? I mean, if you need to do custom busing to existing switchgear, I'm not saying that AIS is never the right option. If you're doing custom busing, if your facility required maintenance practices require a withdrawable circuit breaker, then AIS may still be the right option for you. So AIS is not completely out of the option. What I think my main goal here is to basically give you guys more tools in your tool belt when you're doing designs, depending on your customer, their requirements, and the facility that this is going to be going into. How about switchgear depth? Metal clad is pretty much always going to be the deepest. You're always looking at something like 90 to 100 inches deep for NEMA 1 indoor style metal clad. When we look at gas insulated, usually we're shrinking to between 50 and 60 inches deep. And when we go to SIS, solid insulated switchgear, we can get as shallow as 36 inches. So that's kind of the range of depths. How do you compare life expectancy, AIS, GIS, and SIS? So this involves, I have to explain something a little bit. And when manufacturers publish, when they give out a published life expectancy on switchgear, normally what they're doing is they're finding a midpoint in that product life cycle bathtub curve that you may remember from an economics class or from an engineering economics class. Where we're trying to find what is the midpoint expected life of a piece of gear. Some will go quite a bit before that, or some will last quite a bit longer than that. Some will fail earlier than that, depending on the environmental ratings and things like that. But when you look at the midpoint of published life expectancy for traditional metal clad switchgear, most manufacturers publish a 20 to 25 year life expectancy. And I point this out specifically because all of us have probably seen applications where metal clad has been sitting out there for 50 years and keeps working. I say all this to give you an impression that published life expectancy is really a way to compare gear to gear. It's not necessarily a definitive, it's going to last 25 years and immediately die on you. It's more a statistical analysis of life expectancy. So all that, once that's explained, now I can explain that traditional metal clad switchgear is published between 20 and 25 years published life expectancy. Solid insulated switchgear and gas insulated switchgear, all the published life expectancies I've seen have been 30 years plus, depending on the type of manufacturer and the type of switchgear. So generally you're going to get at least a 20%, if not more, upgrade, I'll say, in life expectancy to move to newer styles of switchgear. What are the BIL and short circuit withstand differences between 15 kV AIS and SIS? So with 15 kV AIS, the BIL levels are going to be the same, because BIL is it's a rating that's associated with voltage class. So at 15 kV, according to the metal enclosed standards, the BIL level of the switchgear needs to be 95 kV BIL. The only place I see discrepancy in this is when we get into the 38 kV, because there is some requirements from some customers to go beyond what's recommended in the ANSI IEEE standards. When we talk about short circuit classes, short circuit levels, interrupting short circuit levels of AIS go all the way up to 63 Ka. So you have a really broad range of short circuit interrupting ratings. SIS, the ones that I'm familiar with, go up to 25 kA. So in general, it covers about half of the general industrial market in terms of what's required. Oftentimes, we find that customers are quoting or are asking for 40 kA or 50 kA, but when we do an actual short circuit study, we're finding that their interrupting ratings are in the 15 to 20 kA range. And this is important mainly because of cost. If you're asking for a 40 or a 50 kA circuit breaker, but you only require a 15 kA circuit breaker, especially if you're asking for a 50 kA circuit breaker, you're going to be paying double for that circuit breaker versus what you could have used at 25 kA in order to satisfy that rating. So I say all that to encourage you to make sure that you're asking for the interrupting ratings that are actually applicable on your projects. So good question there. What is the recommended test period for the metal enclosed switchgear annually? Yes, traditional metal enclosed switchgear is recommended by most manufacturers to be tested annually. Some manufacturers, I think, have a 3-year recommendation in their O&M manuals. But again, generally 1 to 3 years is the recommended rating. Now, that being said, you should always go off the recommended ratings of the manufacturer of the switchgear that you have. So I would encourage you to check that in the O&M manuals for whatever manufacturer of switchgear that you do have. For SIS, let's see, I think we're almost out of time. Let me double check the time. Oh, we're actually over. So this is going to be my last question, and then I'll give it back to Jim, and I'll take a look at the rest of the questions and maybe get you guys some answers after that. So for SIS gear, would I need to shut down the entire switchgear to change a feeder circuit breaker? Yes. So that is one of the biggest differences with GIS and SIS is if you ever need to change out that circuit breaker, you have to shut down the bus and remove that cubicle and install a new cubicle. That's one of the biggest drawbacks to fixed mounted circuit breakers. Now again, I want to emphasize that the whole point of a fixed mounted circuit breaker is you're removing all those major failure points that cause circuit breakers and metal clad switchgear to fail. Things like environmental exposure, things like corrosion of the exposed vacuum bottles, all of those things are, since it's in a completely enclosed and sealed tank for life inside of the switchgear, all of those main causes of failure go away. So the difference is a design philosophy of preventing the failure as opposed to giving ease of maintenance. So keep that in mind. Good question there. So with that, I'm going to close up and shoot it back over to Jim. Thank you all for your time and for listening to this presentation.
Good job, Joe. Thanks a lot. I just wanted to leave the folks with the reminder that somewhere between 7 and 10 days, we will have a copy of the video posted on the website along with a copy of the presentation. So thanks to everyone and hope you have a good day.